Okay, so I showed you a way how to estimate an unknown parameter for a probabilistic model based on maximum likelihood if you observe data. Now, is this a good way or not? That's actually not that obvious question how one would even answer that, because clearly one will not hit the perfect value. And the other thing to keep in mind is that whenever you estimate a quantity based on data, if this data is from some random process, then the estimate will also be random. So first, what you have to do before you think about is my estimator a good estimator, you need to know what an estimator is. So an estimator is, it's not the value that gets out. Typically an estimator is a rule for calculating a certain estimate, which is a value, E hat, of an unknown quantity E based on observed data. So in particular, it's a rule given the data how to get an estimate of the quantity. If your input data is random from some distribution, then the output will also be random. Right? But then we can ask some questions about estimators and what they do and what they don't do. So the first thing we can do is, well, if this is a random quantity that fluctuates a little bit up and down, if I see samples from a Gaussian distribution, then and I estimate the mean from them, then sometimes I will overestimate the mean, sometimes I will underestimate the mean. That is unavoidable. But I can ask, well, an expectation over all possible estimates that I make. Do at least on average, on expectation, I get the right thing. And that's called the bias of an estimator. So the bias of an estimator is you compute the estimator for every possible data that is given to you, and then you take expectation over that data. Since the data is sampled from a distribution itself, this sample set is a random variable. Estimator of that is a function. You can compute the function, the expected value of the function under the true distribution of the data. So this will just be a number again. I mean, whatever the E is, this is as well. And then we can check, is this, on average, the expectation of our estimate the same as the actual quantity we care about? And if they are the same, we call the estimator unbiased, and then and otherwise we call it biased. If it's unbiased, that you can really think of your estimator as fluctuating around because you didn't have infinite data observed, but if you just would have enough, it fluctuates around the mean somehow. So unbiased is good. The other thing we can think of is, well, if it fluctuates around the mean, how wide is the fluctuation? So how far on average is my estimate from the true quantity? Or how far is it from its own mean? So what we can do is we can compute the value we actually get for a certain sample set minus the expected value of that, so the around which value the estimator fluctuates, and then we can compute the squared distance between those. And if we take expectation over all possible sets again that we could observe, we have computed the variance of the estimator. And if the variance is large, that means observed on some data, we get sometimes large fluctuations around the true value. And if the variance is small, that means we vary only slightly little bit around the true data. So here's an illustration for all that. That is, it's good to keep in mind if you ever have to estimate stuff from data. So clearly it's good to have a small or no bias, right? If you're roughly at the center of the thing where you want to be, that's good. And it's also good to have a really small variance because then you really, you don't deviate too much from what you really want. Sometimes it's not possible to have both at the same time. And then what should you do? So here's an illustration of what's going on for different situations of noise and variance. In the columns, you have different amounts of variance from low to high. In the rows, you have different amounts of noise from low to high. Top left, low variance, low noise, means you're spot on basically always, right? So you have, like the center of your values is exactly the right center, and the spread is really small, so that means you must be on the center almost all the time. If you go down, you still have very small variance. The differences of values doesn't change much over different instances of your estimate. But the center moves around. So the middle one is biased. It doesn't really center around the true value anymore. It centers around something else. And then the bottom one is highly biased. So it has a small variance, but unfortunately at the wrong location. Yes.
Can't we just correct for bias if we know which direction it goes?
But we don't know that because we don't know the true value. The main problem is we do not know what the true value is, right? If we would know what the true value is, so this is, I mean...
But if we know nothing about the bias, then how do we do the trade-off, right?
One good question, yes. So you can sometimes say things about the bias of an estimator without actually being able to compute it, right? So you can maybe say the bias grows like square root of n, and then you know that, well, we're not going to talk about this very much, but you can like prove statements about bias of estimators. Basically, what you want to construct an estimator in the first place that is not biased.
So we can prove something about the size of the bias
yes.
without knowing anything about the
yes.
iteration.
Yes. In fact, okay, I'm going to talk about that in a second. The other direction is, even if you have no bias, so you center around the right point, if you go further to the right, if your spread is gigantic such that it's around the right point, but almost always far away, then your estimator wasn't very useful either. And in the end, what you might be able to, it might be better to accept an estimator that has a certain bias, but not too much, but if its variance is also small. So maybe the point in the middle here is preferable to that situation. So yes, you're not spot on. Usually you're far. You have a certain distance from the true value, but at least you're never 5 kilometers away, or maybe somewhere in between. So this is of course just a schematic, but it's good to keep in mind that sometimes, so being only unbiased is not enough if your variance is huge, and the other way around as well. So one thing that we'll see in a second is it can be good to have if you start with an unbiased estimator, it might be worth making it a little bit biased in order to reduce its variance. So that is one important part of estimator theory that I'm not going to talk about. So sometimes it's better to use a slightly biased estimator than an unbiased one, because the variance would kill you otherwise. Okay, so if we already know that an estimator is unbiased, so it's spot on in the expectation, and then it will still depend how much data we've seen, what its variance is. So typically, if you have more data, the variance goes down. And if you have an estimator that is unbiased and its variance converges to 0 when the size of the data that you've seen goes to infinity, then we call it a consistent estimator, and that's the one you love the most. So these are the ones that are like, if you just observe enough data, you know it'll converge to the right thing. If something is not consistent, then even in infinite data limit, you wouldn't know if you have, it wouldn't converge necessarily to the right thing. That's not a good thing to have. Why do I introduce these terms? Well, because the maximum likelihood estimator is actually unbiased under some conditions. So if your data comes from a distribution which you can represent with your model class, so if your model is Gaussian and your data also is actually Gaussian, then maximum likelihood is a consistent estimator. So in the limit, it will converge to the true parameters of your model, which is a good thing. It's not obvious how to prove that, but it's a good thing. So that means in particular, if you have really, really, really a lot of data, maximum likelihood is often a good thing to do. So what if your distribution of the real world is not of the class of models? So if you have a Gaussian model that you try to fit, but your data is not Gaussian, it can't be consistent because there is not even a true parameter that it would fit, right? It cannot go to the right parameter if there is no right parameter. So if your data is misspecified, if your model doesn't correspond to the real data out there, maximum likelihood, there's no guarantees that maximum likelihood is a particularly good idea. It's still usually good, but it's not, provable. Okay, that's maximum likelihood. So what else is out there? The next thing we want, that is a very important class of estimating quantities, maybe even more important, is maximum a posteriori estimation. And that is based on the idea that, what is theta? Theta is, so far we treat it as a fixed value of our model, right? But we don't know what it is. So by our very much introduction, if we have something, but we don't know what it is, we are uncertain about it, shouldn't be treated as a random variable, right? Isn't that what random variables are all about? It's quantities for which we don't have enough information to specify them exactly. So let's treat this unknown parameter theta as a random variable and see what comes out. So we know that for any fixed value of theta, we have a distribution over the axis. That's our probabilistic model. So that corresponds to the model where conditioned on a value of theta, we get a probability. So that would be that our original model is a conditional model for fixed theta. So we're going to write P of x given theta for our model. And then what are we interested in? Well, given some data, we have additional information. In the beginning, we don't know anything about our parameter. If we observe data, then we accumulate more and more information, hopefully, about what our parameter is. So what we want to do is we want to use the available data in order to specify where our parameter can live. So we want the distribution of the parameter conditioned on the observed data. So that's the distribution of theta given x1 to xn. And we can actually compute that using Bayes' rule. So probability of theta given all the x's by Bayes' rule is the probability of all the x's given theta times P of theta over the probability of the x's themselves. Now, what is the best value of theta? Well, we can say it's the one that is the most likely parameter value, because now we have a distribution over parameter values. Each possible value has a certain each parameter value has a probability. Let's take the most likely one. That means we have to maximize the probability of theta given the x's. The good thing is that if we maximize this expression, we have to maximize this expression, which is a ratio. But the ratio, the denominator of the ratio doesn't depend on the theta. So we can also just optimize the numerator instead. So we have to maximize the product of the x given the theta times P of theta. Now we know that our data was independent, so the product of all the x's given theta is just the product of x's given theta multiplied. So what we end up with is an expression that is the maximum of, we take the probability of our data given theta, that should not be a bracket, that should be just conditioned, multiplying it over all data points, multiplying it with the prior, that is the expression we have to maximize. Or equivalently, we take logarithm of that, and then we have to maximize the sum of logarithm of the distribution of the prior distribution of the theta, and sum of the data terms. And the second term we've already seen, it's the sum over the logarithm of the probabilities given theta. That's the data log likelihood, the one we optimized before in maximal likelihood. So the only thing new is that we now have also an additive term that is P of logarithm of P of theta. So what is logarithm of P of theta? Well, it's prior over which values of parameter we find likely. Right? It's our, before even having seen any data, which parameters are likely to occur. It's not something we can estimate because it has to be specified before we see any data. So it's our design choice. Which values do we think make sense? So for coin toss, what do we need to specify? We need to specify what's the probability of any probability of heads or tails. Theta was how likely is it to see heads. So what value should we think is likely for that to happen and what value is unlikely for that to happen? For example, you can think, well, all values are equally likely. That would mean the distribution over theta without any data is just constant 1 because, I mean, it's a constant and it has to integrate to 1 over the interval 0, 1, so it happens to be 1. And then we can plug that into our expression here. We will have to maximize logarithm of this prior probability plus the data likelihood. The logarithm of this will actually be 0 because it's log of 1 for every possible value. It's a constant. So we will end up with just maximizing the data likelihood, and we end up with the same thing as we had before. Count how often the heads occur, and then that's it. So if your prior doesn't have any preference for one value or the other, this kind of estimation will just give you back your maximum likelihood estimate. But you might insert some knowledge. So for example, you might think that it's really, really hard to build a coin that always lands on one side. So maybe it's much more likely that it's somewhere near 1/2, right? So we can have a prior that is more likely to have parameter values near 1/2 and much less likely to have parameter values at 0 or 1. So in a drawing, instead of the flat thing that says all values are equally likely, the red curve, we would have like the blue curve, which says maybe this is a better distribution for our belief what the prior should be. And then what comes out is that the the parameter value that has the highest probability under this model is not the counts anymore, but it's a variation of it where you take the count plus 1 and you divide by n plus 2 instead of n plus 1. So you get a slightly different estimate. And then you could also do other stuff, right? You can do any prior you want, whatever you believe in. So you could say, well, I do believe 1/2 is more likely, but I don't believe in this roundish shape, which happens to be theta times 1 minus theta as a distribution. I believe in nice straight lines. So I think 1/2 should have the value 2, and it should go linearly down the probability outside. For sure, if you like that. Then you can try to maximize the probability of the theta given the data, given this prior, and you will most likely not have an easy form of what comes out. So the change of the prior, instead of a very easy rule how to compute the estimate, now will be some kind of difficult numerical procedure that I didn't even want to try. So the choice of prior influences not just the value you get, but also how easy it will be to get that value. Okay, so that is a general rule for if you want to do this kind of probabilistic reasoning about parameters, the prior has to reflect our knowledge, sure, but it should also not make the computations completely intractable. If we come up with a really complex thing, which parameters are likely and which ones are not, then we cannot compute these things anymore. So, and people came up with a smart idea what to do. So they said, try to use a prior such that the posterior of the value given x, so how the distribution of x of theta changes when we observe data, has the same parametric form as the prior that we started with. So in the coin example, the probability of our data is parameter to the number of counts multiplied with 1 minus parameter to the number of counts of the other option. And then if you choose a prior that has a similar form, so it's also going to be parameter to some power 1 minus parameter to some power. Then when you compute the posterior distribution of parameter given data, you know that this is proportional to these two terms, the data likelihood and the probability of the theta itself, up to a normalizing constant. Well, then you will just normalize theta to some, multiply theta with some power to another theta with some power, so that turns into theta with some power. And you multiply 1 minus theta with some power to 1 minus theta with some power, that turns into 1 minus theta to some power. So you haven't changed really the parametric form, you just changed the values that occur in the exponent. And if this is the case that by going from the prior to the probability of the parameter given the data, the parametric form doesn't change, we call it a conjugate prior, and these are very nice things to have. So for this coin toss example, it's called a beta distribution. So any distribution of this form, something to the power 1 minus something to the power is called beta distribution, and the beta distribution with some parameter is the conjugate prior to our coin probabilities. The nice thing is, in that case, you can still write down a nice closed form expression how to estimate the parameter, in this case, number of outcomes plus a minus 1 and so on. Two special cases we've seen. If we would choose our beta distribution with a equals 0 and b equals 0, that means we have theta to the 0 and 1 to the theta to the 0, so that means our p is constant. That's the case where we had no preference for any values, and the other where we had this like round shape with a peak at 1/2 that corresponded to a equals 2 and b equals 2, and in general you can express many different shapes of your belief in this form of a beta distribution. Okay, now being at HSE, there is no way that I will not I cannot talk about a real Bayesian treatment of these things. What we did so far is point estimates. All the data, lots of probabilities, but in the end we end up with one number. Right? That feels wasteful. Don't we have much more information in a distribution of values than in just one number? So can we do something more than just coming up with a number? So maybe the distribution of thetas that we get, given the data, contains more information than just where its maximum is. So we know already that it's a beta distribution because it has this form, something to a power 1 minus something to a power. So it will look like one of these guys. So these are examples of different beta distributions depending on what your exponents were. So these are the counts and also whatever you put in as a prior. So let's look at one of them. happens to be alpha equals 2, beta equals 5, but that doesn't really matter. If you pick one of these beta distributions, they typically look something like this. So the first thing you see that this is a highly non-symmetric distribution. Right? So the maximum is here, that's true. But then there's a much more probability mass on the right than to the left of the maximum. Right? So if we do this map estimation, the maximum of the posterior, we would say where's the value the highest? But we might ignore that there's a high chance of much bigger values occurring at all. So what instead you can do is you can look at other characteristics of the posterior. So not just the maximum, for which we have this closed form expression. You can look at the median, right? So at which point are half the value above and half the value below my estimate? That would be actually a different value. Instead of 0.2, you would estimate 0.6 then. It's the yellow dot, I guess. You can also just say, okay, I have a curve. Now, what's my expected value for the parameter under this distribution? And then I get yet another value, it's 0.28. So again, the distribution tells you better go further to the right because there's a chance of really high values that you would have ignored otherwise. And if you do a Bayesian treatment of many things, it's very often that you take this mean, so the expected value of your parameter under the distribution that you estimate for the parameter. One of the reasons you use that is because you can compute it using samples and so on. I mean, I cannot do that, but true Bayesians can do that. Okay, so now which one is the best? Who likes the maximum posterior best? Who likes maximum likelihood? Who likes the Bayesian? Who doesn't like any estimation theory and wants me to move to something else? I don't believe you. Okay, so what are pros and cons? Well, maximum likelihood is usually the easiest. If the model is correct, it's a consistent estimator, that's good. It's harder to include any kind of additional knowledge that we have. And if we have very little data, it tends to be overconfident. So for example, if you flip a coin once, maximum likelihood, and it happens to be head, maximum likelihood will tell you the probability of head is 100%, the probability of tail is 0%. From now on, it's always impossible that tails will happen because I saw one head. It's a bit overconfident, right? Actually, there's a, okay. About these reasonable ranges, there's a nice anecdote where when you estimate the mass of the neutrino, as far as I know, I'm not a physicist, you do not estimate the mass itself, you estimate the square of the mass. And when you look at the values that you derive for the square of the mass, many of them happen to be negative. So if you just do maximum likelihood, you would get a negative mass, negative value for the square of the mass. As I said, I'm not a physicist, but this sounds fishy.
Must be irrational. Must be an irrational number.
Apparently. What to do instead is you put in that you know that your values fluctuate, but clearly you know that your mass is a positive quantity, or at least the square of the mass is a positive quantity. So you put in a prior that says negative squares do not exist, and then what you will end up is a much better estimate of what's actually going on. So sometimes you have prior knowledge about the reasonable range of values that maximum likelihood would not be able to make use of. So maximum posterior, you can include a prior, for example, ranges of your parameters. It's maybe more robust in case when you specify a prior and you have very little data on top, it will stay close to the prior. On the other hand, how do you choose a prior? That's not always clear. It's up to you. And it's typically computationally a bit more challenging because, I mean, especially if you don't use this trick of a conjugate prior, then you often, I mean, it's much harder to get the distribution over thetas than just the maximum likelihood. Bayesian has the same advantages and disadvantages as the maximum posterior, except that instead of just keeping one value, you would try to really analyze the whole distribution, which can be even more challenging computationally. On the other hand, sometimes you can do the Bayesian thing because you know how to generate samples from something where you wouldn't be able to find the maximum peak of your distribution over thetas, but you will be able to compute the expected value. So sometimes it's easier than map. I don't think it's ever easier than maximum likelihood. The other thing to keep in mind is if your data goes to infinity, then typically the prior stops mattering and everything converges to the same thing. So if you have really, really a lot of data, maximum likelihood most likely is as good as anything else. Okay, so now I told you about coin tosses. That's not why we're here for. We're here for graphical models. So how do we estimate parameters for graphical models? We follow exactly the same procedure. So the easiest to do, let's do maximum likelihood for directed graphical models, belief networks. So we are having a graphical model, it's a simple one, 3 terms, 3 binary variables, A, C, and S. Based on this graph, you know what the corresponding distribution is. So you should be able to do that in your sleep now. So it must be a product of 3 terms, P of A, P of S, and P of C given its parents. So P of C given AS. And now, what kind of parameters does this model have? What do we have to learn? Well, it's exactly the values of these probabilities, right? We know that they exist, but we don't know what their values are so far. So it's essentially these probability tables. What's P of A equals 1? What's P of A equals 0? What's P of C equals 1, given that A is 0 and S is 0? These kind of things. So there will be 6 unknown parameters in this model. It's theta A, as we call it. It's the probability of A being 1 in this X term. And then A equals 0 is just 1 minus that, because we only have 2 possible states. We have another parameter that is the same for S. And then we have one parameter which has 4 parts. For each possible thing to conditioning on, it's the probability that the C will be 1 if we condition on the indicated values. The probability that C equals 0 we don't need, because it's 1 minus the probability that it's 1 conditioning on the same stuff. So how do we do that? Well, if we observe data, that will be tuples of A, S's, and C's. Each of them follows the graphical model. If we want to, we can repeat our exercise of plate notation. So we have n copies of this model, but then the parameter is actually outside of the model. So there's one parameter, and it influences all the outcomes of the n observations. I don't know why these parameters are now little dots instead of big dots. What do? We do maximum likelihood. So we write down the likelihood of our model. It's this exactly probability, and then the log likelihood is the sum of these logarithms summed over all data points. So we can use the rules of the logarithm, that the log of the product is the sum of the logs. And what we end up with is, well, this sum should be over everything, of course, sorry. Okay, so now what do? We have to maximize this expression. One convenient way of writing this in an easier way is to introduce counts again. So we just count how often each outcome occurs. How often does the combination 0, 0, 0 occur? We call that n 0, 0, 0. How often does 0, 1, 0 occur? We call that n 0, 1, 0, and so on. And then with trick that I introduced last time, that if we have a sum over many terms, we don't have to introduce as many terms as they are, but we can just count how often each possible value occur with a multiple in front of it. So we'll be able to rewrite the log likelihood as all combinations that occur. So for A, only 0 or 1 can occur, and the 0 occurs, well, n 0 times, and the 1 occurs n 1 times. So the sum over all these guys will just be n 0 times this plus n 0 times that. For the S, the sum over all the S's will decompose in the same way into the counts and the probability log itself. And for the last sum that has all these conditionings, well, we have to count how often all the variables with each other occur. These probabilities was exactly what our parameters of the models were called, right? So we can rewrite this in terms of the unknown parameters, and we have number of zeros, logarithm of 1 minus the parameter, plus number of ones, logarithm of the parameter. Where's my logarithm? Yeah, sorry, there's a logarithm missing here. And so on. So we just spread the terms through. The first thing we observe is that these parameters do not interact with each other at all. So we can choose each of them freely without looking at the other ones. It's not that they have to sum up to something or that they must all fulfill some properties. So we can look at each of them separately, and that means we can also optimize for each of them separately. So for example, we pick one of them. Let's pick the probability of C being 1, given that A equals 1 and S equals 0. Then the terms where this shows up in the log likelihood is just 2 of them, one where C ended up 1 and one where C ended up 0. We take the derivative, we set it to 0, and if there's no sign error, what we get is the maximum likelihood parameter of this probability table that we want to estimate is how often did the combination 1, 0, 1 occur, divided by how often did 1, 0, 0 plus 1, 0, 1 occur. What is that? Well, it's the same as what we had for the coin. We just count how often the outcome 1 occurred in a certain situation, and we divide it by all possible values that could come out in this situation. The situation in this case is what is the value of A and S, and the outcome is the C, because we have the probability C given the other two. So we just had to count outcomes, divide by the right number, put it into our table. If we do that for all parameters, we have the maximum likelihood of the graphical model. So it's nothing different than if we only want to estimate one quantity. Now we want to estimate all the individual quantities. So if we do that in practice, we just have to count how often does a 1 occur in this list of examples, and then we divide it by the total number of examples. That's 4 over 7, so 0.57, and so on. And these are the other estimates that are read off from this table, right? So this one is how often does the combination 1, 0, 1 occur? Once. How often does the combination 1, 0 with an arbitrary third occur? 1, 2. So it's 1 over 2, 1/2. Trivial. Maximum likelihood for conditional probability tables is really not hard. Was that a coincidence? No, this is what always happens when you try to estimate these things from data and you do the maximum likelihood approach. For every belief network that factorizes in this way, it's actually not hard to show that this is the case. If we go back to the previous observation that maximum likelihood is also the same as minimizing the KL divergence between the empirical distribution and the model distribution. So how do we minimize the difference between the empirical distribution and the model distribution? If we can choose all values in our model distribution arbitrarily, we set them the same. If we set all the empirical distribution, if we set our model to exactly the same as the empirical, they are the same. And this counting exactly sets our probability to the empirical observations. So KL divergence is 0, we can't get any better than that. Now that is if you have discrete values and you have small enough state space that you can enumerate, that you really have all parameterizations. There's a few situations where this is not practical. So for example, your tables might be too large. If you have a graphical model like this, where one conditional variable is conditioned on many, many parents, then you will get an exponentially many states that you have to count. And first of all, you don't want to store all of these exponentially many values. And second, you might not have enough data to estimate them, so most of them will never occur. And then there will be 0, as we saw. And having zeros in our model is typically not good. The other thing that can happen is that you have continuous variables. Then, of course, you cannot just count the outcomes. Or you have missing observations. So the counting only works if you see all of them at the same time. If there's some values missing, like in the hidden Markov model we saw before, we only observed some parts, like the radar signal, but we did not observe the true position in the sky. In that case, none of these methods, counting is not enough. And you will need some other method. You would still write down maximum likelihood, but you would not be able to just get the result by counting. You would have to actually take derivatives and do some gradient descent, but we're going to talk about these kind of methods later anyway. Okay. You like Bayesian, right? I think it's your job to like Bayesians here. You don't have to do maximum likelihood. You can also learn Bayesian belief networks using Bayesian reasoning, of course. I'm going to be fast about this. So how would we do a Bayesian approach to this? Well, we have to define a parameterization. We can use the same parameterization as before. So in this model, we would have these 6 unknown parameters. Then we need to define a prior on these parameters. And then we have to compute the posterior distribution of the unknown parameters given the data. So we have 6 parameters as before. Now we have to define a distribution over them. So the easiest would be to assume, well, let's assume that they are independent of each other in the groups. So the A parameters are independent of the S parameters, are independent of the C parameters. So the prior of all three together is the product of the three. We can also be more extreme and we can say, well, even within the C, which has 4 parts, they are all independent of each other if we like. Priors, our choice. If you want to draw this as a graphical model, now you have these random variables, which are your parameters, right? And then you have n copies of the data that you observe. And then you also have priors here. So there is 4 unknown parameters that influence the C variable. So you have 4 copies of a random variable here. I mean, we could also have written all 4, but this is the plate notation that influence the C. And now we can just use the tools of graphical models. So we get a joint distribution over all our things. Well, we follow the rules and we say the joint distribution over everything will be the product of this conditioned on that, this conditioned on that, this conditioned on these two, and that one, and so on and so on. So this model automatically gives us the distribution and how the priors and the data interact. If we do that, we can apply Bayes' rule. We get the distribution over the parameters given the data is proportional to the likelihood times the prior over some constant. You massage the terms a little bit. And what you will get is that if your prior factorized into a product of individual terms, then your posterior distribution over the parameters will also factorize. That just follows from Bayes' rule backwards, taking independence, using it in the other way around, and so on. So these are mechanical steps that you don't have to do now, but they should be true. So that means we can also, if we want to maximize, if we want to look at the distribution of parameters, we can look at the distribution of parameters separately, right? Because it's a product, each term is independent of the other. And now we can do that. What we care about is the product of the data likelihood times the prior, as before. What kind of prior should we choose? Well, it's usually good to do a conjugate prior, right? Because then we can actually still reason about things without doing too much numerics. So again, we choose a beta distribution for our parameters. That means our prior must have this form. And then it's all the same as in the coin example, only now we have, we do it 6 times. Because of this conjugacy, we can actually express all the things nicely. We end up with a posterior distribution. From the posterior distribution, we can compute the expected value of the parameter under the distribution as we did for the coin. And what we'll end up with is this. It'll be some simple ratio of the counts that we observed for ones, the counts that we did for zeros, but with some additional terms that depend on what our prior was. Now we can look at how this behaves under different regimes. What if we have really, really no data? So the number of examples we observe goes to 0. Then this expression, well, the number of counts most likely will go to 0 because there is no data, and we'll end up with this ratio, which happens to be exactly the prior that we plugged in. Whereas if the number of data points goes to infinity, then these numbers get really, really large, and these small constants in return don't really matter anymore. So then we will go to number of counts for A divided by the sum of both outcomes. So that is exactly the maximum likelihood solution again. So with the Bayesian treatment, we have the same property. With very little data, we rather trust our prior. If we have enough data, it will converge to the maximum likelihood solution anyway. So it's like at least a safe way. We're not overconfident with little data, but for large data, we didn't hurt. Okay, and that was my example. The main thing to see is if we do this Bayesian treatment in this example of 7 patients, our estimate for the A is 0.55, whereas for the maximum likelihood we're at 0.57. What does that tell us? Well, the prior tells us to a little bit stay closer to 1/2 because we plugged in a prior that says 1/2 is the more likely prior. So it pushes us a little bit closer to the conservative estimate. Okay, let's skip the part about many different states. You can look it up in the, model. And we have another hour. Let's make a short break, 5 minutes, because now comes a really new part.